Okay, so this is section 11.4, video number 2. We are continuing our idea of the comparison tests for convergence and divergence. The first one was a direct comparison test where you directly compare a function to another function of some kind, and you basically squeeze it one way or the other, pushing it to either be convergent or divergent, depending on what you've already been given. The limit comparison test is going to be a little bit different in that we're really going to be creating a ratio in order to determine this. So I don't necessarily think this is the most intuitive of the two, but I think it's the easier one to actually do the test. So the idea is if we are given an a sub n of some kind, and we come up with a b sub n, as long as they're both, according to this, greater than 0, if you take the limit as n goes to infinity of the ratio of the two series, whether it's a sub n over b sub n or technically b sub n over a sub n, that doesn't really matter, and you get an actual finite value, then what you have is a convergent or a divergent series based upon the one that you pick to compare to. So what do I mean by that? This is why this kind of works. This takes you all the way back to the concept of limits and ratios and common ratios for geometric type series. So if you were to take let's just say a sub n is convergent. If you're to take an a sub n, which is convergent, we don't know that yet, but let's just say that that's what it is, and we pick a b sub n, which is also convergent, the way the ratio of these two things is going to work is because if they are both convergent, then they're basically going to have the same growth rate. And if they have the same growth rate when you take the limit, you should end up with a finite limit, a finite value. If you were to compare it to something that doesn't have the same growth rate, then you're either going to get 0, which is inconclusive, or you're going to get infinity, which is not going to help us either. So what you need to do basically is find a b sub n that has the same growth rate as your a sub n, and then whatever your b sub n does, whether it converges or diverges, then a sub n will do the same thing. Again, you have to end up with a finite limit. Okay, believe it or not, even after explaining all that stuff, it doesn't sound that simple, but it is not. It's not really that difficult. So what you're going to do, again, you're still going to hypothesize. What do I think is going to happen here? And then you're going to basically try and find a simpler b sub n to compare it to. And once you do that, you'll take the limit of the ratio of the two. And then if the limit either equals 0 or doesn't exist, the comparison test is inconclusive. Anything else that's a finite value tells you that the series either both converge or both diverge based upon your b sub n. So again, I do think this one's easier. Let's kind of show that it actually is instead of me talking about it. Quick little reminder, your basic p series. Remember that if it's 1 over n to the p power, p is greater than 1, it converges. P is basically less than or equal to 1, it's going to diverge. The limit comparison test is really good for, and it says up here, messy algebraic series with a p series. It's really good for power functions specifically. Those are the easiest ones. So if you look at the first 3 examples there, they all have things where n would basically be raised to a constant power of some kind. Then you could compare them. So just for example, if you look at the very first one, 1 over 3n squared minus 4n plus 5, the dominant powers in the numerator and the denominator are what you're looking at here. The dominant term in the top is 1, so it stays the same. The dominant term in the denominator is the 3n squared, so we're going to compare it to an n squared in the denominator. The coefficient there doesn't make that much of a difference. If you look at the second one, again, the dominant part in the numerator is still 1. The dominant part in the denominator is the square root of n part. So that's why that's the comparison. And then in the last one, which is probably the more important one, the dominant term on top is n squared. The dominant term on the bottom is 4n to the 5th. So if you compare n squared over n to the 5th, it simplifies to 1 over n cubed. that would be your B sub n. Again, this is not really that difficult to do. You'll see. So let's determine the convergence or the divergence of the square root of n over n squared plus 1, and that's the sum as n goes from 1 to infinity. So you basically want to say, okay, well, this is our a sub n. Our b sub n should be, looking at the dominant term on top, n to the 1/2 power divided by n squared. Now you do have to simplify that. Well, you don't have to, but it makes it a lot easier. So that would be the same thing as, remember, you would subtract the exponents, so n to the 1/2 over n squared is going to simplify to 1 over n to the 3/2 power. So that's going to be our b sub n. Well, what do we know about b sub n? This is a p series. P is 3/2, which is greater than 1, which means that b sub n is convergent. So now, if we take the limit as n goes to infinity of a sub n over b sub n, or b sub n over a sub n, that order doesn't really matter. And if this limit gives us any kind of a finite value, because b sub n converges, a sub n will also converge. So let's go ahead and find this limit. So a sub n was the square root of n over n squared plus 1. And now remember, when you divide by b sub n, you're dividing by 1 over n to the 3/2. It's multiplying by its reciprocal, so this will be times n to the 3/2 over 1. And if you were to distribute all this stuff out, which you don't actually have to do that portion, but I'll do it in this case, you would get the limit of the numerator would be n to the 1/2 times n to the 3/2, which is n to the 4/2, or n squared, over n squared plus 1. And we know that that limit is 1 because the growth rates are the same on the top and the bottom, meaning that you can divide the leading coefficients and we get 1. 1 is a finite value, therefore a sub n is also convergent. So again, the idea here is we are comparing this by using limits to something which has exactly the same overall growth rate. So whatever one does, the other has to do the same thing because they're growing at the same rate. All right, number 2. So we've got 5n squared plus 9 over 7n cubed minus 2n plus 8. Again, if you make a hypothesis, looking at your dominant terms, you would have an n squared over n cubed, which is going to reduce to 1 over n. 1 over n is the harmonic, which is divergent. So we would expect this to be divergent. Let's see if that's really the case. So we are going to say that this is our a sub n. We'll call b sub n. Again, I just did it. The n squared over n cubed will reduce to 1 over n. So we'll call that 1 over n. So n goes from 1 to infinity. And we know that this is the harmonic, or basically a p series where p is 1, same thing, and therefore divergent. So now let's take the limit and see what we get. The limit as n goes to infinity, again, doesn't matter which order you divide these in, so I'm just going to start with a sub n here, 5n squared plus 9 over 7n cubed minus 2n plus 8. And we'll multiply it by the reciprocal of 1 over n, which is n over 1. Now, if you were to distribute, in this case, I'm not actually going to do it. If you were to distribute the n through the top, you would get a 5n cubed as your dominant term. So then you'd have a 5n cubed over a 7n cubed, n cubed, same growth rate. Just divide the leading coefficients, and you would get the limit to be 5/7, which is a finite value. And since it's a finite value, A sub n will do the same thing as B sub n, so A sub n is divergent, just like we hypothesized. All right, moving on. Determine the convergence or divergence of the sum of n plus 2 over the cube root of n squared minus 3n plus 5. So again, the dominant term on top is n. Again, here we're going to call this A sub n. Our B sub n will be, n goes from 1 to infinity. The dominant term on top is n. The dominant term in the denominator is going to be that n squared under the cube root, so it's going to be n to the 2/3 power, which will reduce to the sum, the n to the first over n to the 2/3, which is the same thing as n to the 1/3 power. So n to the 1/3 power, it's not even a fraction, it's just going to keep on getting bigger and bigger, so we know that that one is going to be divergent. And when you get something like this, you might actually go back and say, was there an easier way? And yes, there certainly was, because if you were to just apply the limit test, which is probably what we should have done in the beginning, the limit of this particular original series, A sub n, would have gone to something which is not 0, which means it would have been divergent, and there was no reason to do a comparison test. So once I got to that point, I'm like, okay, this is not even going to work for I mean, it still works for the comparison test, but it's not even necessary. I'm just going to go back and say, well, wait a minute, the limit of n plus 2 over the cube root of n squared minus 3n plus 5 is infinite, because the numerator grows faster than the denominator, and therefore A sub n here is divergent. Okay, I didn't even have to finish the whole limit comparison test there. It still would have worked, but you don't have to do it. All right, determine the convergence or divergence. Now we've got some exponentials here going on in this. So the dominant terms are exponential. Again, if your hypothesis should be that the denominator is going to grow much faster than the numerator because it's 5 to the n on the denominator, 3 to the n on the numerator, it should converge. Well, we're going to test it and see. So this is our A sub n. Our B sub n is going to be taking the dominant terms on the numerator and denominator. We've got 3 to the n on the top, 5 to the n in the denominator. So that'll be 3/5 all to the n power. Okay, that one is a geometric, where r is 3/5. 3/5 is less than 1. Therefore, this one is a convergent series. So now our B sub n is convergent. So what we're going to do is we're going to take our limit as n goes to infinity of 3 to the n plus 6 over 5 to the n plus 1, and we're going to multiply that by the reciprocal of 5 to the n over 3 to the n, and we're going to see what we get here for our limit. All right, this one takes a little bit of extra work. So this is going to become the limit as n goes to infinity. So I've got two numbers, 3 to the n and 5 to the n, being multiplied when I distribute these things through the top and the bottom. The 5 to the n on the top is going to give me a 15 to the n plus, and unfortunately you can't do anything with the 6 times the 5 to the n, so you literally just have to write it out as 6 times 5 to the n. Those two things cannot be combined because exponents are not the same. And then denominator will also have a 15 to the n, and then we're going to have a plus 3 to the n, or 1 times 3 to the n. All right, kind of still looks messy, but what you should notice is that your dominant terms are going to be the 15 to the ends on the top and the bottom. And ultimately, your leading coefficient of each one of those would be 1. So what you're going to get is a limit of 1. If you really want to do this the right way, you would actually divide the top and the bottom both by 15 to the n power. Simplify everything, it still works out to be 1. So that means a sub n is also convergent. All right, a couple more examples, and then we are done with the comparison tests. All right, so we want to determine the convergence or divergence of 1 over square root of n plus 1 plus square root of n plus 2. No way to split that one, so you can't split the denominators. You just have to take it as it is. But what it looks to me like, of course, this is our a sub n. What it looks to me like is b sub n would be, the dominant term on top is still 1. The dominant term in the denominator is a square root of n. You have 2 of them being added together, but the fact that you would say it's 2 square roots of n doesn't really make any difference because that 2 could be pulled out as a constant out in the front of the sum anyway. So we're just going to say that the dominant term is a square root of n, which is a p-series where p is 1/2. 1/2 is less than 1, and therefore this p-series is divergent. It really should make sense, because if you have this a sub n 1 over the square root of n plus something or whatever, it resembles a p-series, and it looks like it's probably not going to grow fast enough to be convergent. So let's compare them. Limit as n goes to infinity of a sub n first, which is 1 over square root of n plus 1 plus the square root of n plus 2 times the reciprocal of b sub n, which is square root of n over 1. And again, what you should be able to see here is that your dominant terms on the top and the bottom are a square root of n. So you would take the leading coefficients, and to actually get your limit correct, the leading coefficient of the top one is 1. The leading coefficient of the bottom one, you'd have 1 out in front of each one of your square root of n, so when you add those together, you would actually get 2. Your limit would be 2. Does it really matter ultimately in the end? No, but it is proper mathematics to write the limit correctly. So the limit here is 1/2, which is a finite value, and therefore a sub n is also divergent. All right, one more. And it looks messy, but that's actually why this is a good test to use. We're going to call this our a sub n, b sub n. Let's see, the dominant term on top is going to be that n to the 5th under the square root, so that's really going to be an n to the 5/2 power. The dominant term on the denominator is going to be that n to the 8th, but it's a cube root of that, so it's going to be n to the 8/3 power. And then if you want to actually compare these things, we're going to actually have to make them into common denominators with the fractional exponents. So it looks like 6 would be a common denominator, so it'll be n to the 15/6 divided by n to the 16/6, which is going to reduce to 1 over n to the 1/6, which is a p-series where p is 1/6, which is less than 1. Therefore, that one should be divergent. So now if we compare them by doing the limit as n goes to infinity of a sub n over, oops, still haven't finished writing my a sub n yet, getting ahead of myself, over b sub n, which is the reciprocal, multiplying by the reciprocal, so it is the n to the 1/6, or you could say the 6th root of n, however you want to write it, when you were to multiply these things out, your dominant terms would end up being exactly the same, which means that the leading coefficients give you a limit of 1. And since that is the case, it's a finite value. Therefore, a sub m is also divergent. All right, I think that is plenty enough for this video. Again, I don't think this one is nearly as difficult to do as the direct comparison test, but they are both important and they have different functions. So you should have enough to finish up 11.4.